In this video, we're going to cover sections 8.8 and 8.9. In 8.8, it's just a single slide discussing how we predict the products of an addition reaction. And in 8.9, we're going to start to discuss synthetic strategies. So as you can see, there are basically three factors that are common to all addition reactions. And so in order to predict the products of a particular addition reaction, there's three things that we should consider at all times. So the first thing to consider is what are the identities of the groups being added across the double bond. So we initially started with hydration, so we were adding a hydrogen and an OH group. We've looked at hydrogenation, where we're adding two hydrogens. And we've just recently, in the last video, looked at halogenation, where we're adding two halogens across that double bond. So that's the first important aspect, is to be clear on what we are actually adding across the double bond, what covalent bonds are we forming to new atomic systems. Now, the second aspect that we should consider is regioselectivity. So we discussed the terms Markovnikov and anti-Markovnikov addition to describe the regioselectivity of some of the addition reactions. Now, addition reactions involving water, we saw that we could add water in a Markovnikov or anti-Markovnikov manner, depending on the reagents that we chose. And so under acid catalyzed hydration, oxymercation, demercation, we saw that the OH group, the hydroxyl group, always ended up on the more highly substituted carbon. That is, Markovnikov addition was observed. But when we chose reagents for hydroboration oxidation, we saw the opposite. We saw that the hydroxyl group would end up at the least highly substituted carbon of that original alkene. For hydrogenation and halogenation, it's a moot point because they are identical. You have two hydrogen atoms that are identical, two halogens that are identical. So we don't use the terms Markovnikov and anti-Markovnikov because they're irrelevant in those scenarios. We also spent some time looking at stereospecificity, and primarily with addition reactions, the key aspect is whether or not the reaction observes syn or anti-addition. And so we saw for halogenation, we saw anti-addition, hydrogenation, catalytic hydrogenation, we saw syn addition, and we saw syn addition for hydroboration and oxidation. We didn't see the same stereospecificity with oxymercation demercation because we talked about in passing the scrambling that occurs in that reduction step and that demercation step. And with acid catalyzed hydration, with the carbocation forming as an intermediate, we're going to see a bit of a mixture as well. So those are some aspects that we need to consider. What's being added across the double bond? The placement of those groups, are they regioselective? And then the stereospecificity, are there enantiomers for the products that are being formed? And with syn and anti-addition, it's always important to remember that if you generate two chiral centers in your product, that with syn addition, you'll only observe two of those four. And for anti-addition, you'll also only observe two of those four. So this is where understanding the proposed mechanism can be very helpful, as it provides you with some guidance as to why we observe such product outcomes and product distributions. And so those are the three things that you want to focus on when you're looking at trying to come up with, decide on what are the major products formed from a particular reaction. You have to have some clear sense of the mechanism that takes place in these particular reactions in order to understand the expected regioselectivity and stereospecificity. So now let's look at synthesis. So synthesis strategies or synthetic strategies, in a nutshell, this is what's important about organic chem. This is the largest application of organic chemistry, is to carry out synthesis. And so up until this point, we've looked at many one-step reactions, and I refer to them as one-step reactions generically in that they are functional group transformations. We have one starting material, some reactant, we add some reagents to it, and the net outcome is a particular product. And we've looked at the mechanistic details of how we get from a particular functional group or reactant to a new functional group, our product. With synthetic strategies, with synthesis, we may not be able to choose one set of reaction conditions to get to a particular product. We may need to carry out multiple steps, multiple reactions in order to get to our target molecule or what compound we want to make at the end of a particular sequence of steps. So in order to begin practicing these multi-step synthesis problems, it's important to understand those individual, what we call one-step syntheses. And these are what we've covered up till now. So this slide summarizes the various one-step syntheses that we've covered so far. So we've looked at, initially we looked at substitution reactions, where we can convert one compound to another by changing a particular atomic center or group of atoms. We've looked at elimination reactions, where we've taken alkyl halides specifically or pseudohalides, and we can convert them into alkenes. We saw the same thing for alcohols. If we add acid, we can convert alcohols in a similar manner to give us alkenes as our major product. And just in this current section, we've seen different ways in which we can take the alkene and we can carry out various addition reactions to add different groups across that double bond. So with synthesis, the idea is that we're going to take these individual reactions that we've looked at and we're going to organize them in a particular pattern such that we can obtain a new synthetic outcome or new product that we wouldn't be able to obtain in a single step. Obviously, the ideal would be that everything could be produced in one step, but that's not realistic and not the reality. Is that carrying out the synthesis of natural products, so these are compounds that exist in nature that have medicinal purposes, but to avoid the environmental impacts of harvesting every mussel in the ocean or harvesting every grass in the forest for a particular medicinal purpose, organic chemists come up with a sequence of synthetic steps to produce these fairly complex organic systems. So let's look at some examples of how we can apply synthesis from the reactions that we've learned so far. So in this example, we're going to change the position of a leaving group. Now you can see we have a alkyl halide here, and the net result is also an alkyl halide. The product that we're after is also an alkyl halide. Now the question becomes, how do we get there? How do we get there from our initial reactant to our product? And so typically this will involve multiple steps, and you'll see this type of nomenclature occasionally where there'll be two reaction arrows drawn parallel to one another but slightly offset to imply that there's multiple steps in this reaction. And as you can see below, we could carry out this particular synthesis of this new alkyl halide if we were to first, with our starting alkyl halide, carry out an elimination reaction. So we could carry out an elimination reaction that would get us back to the alkene. We'll discuss how we could do that in just a moment. But in general, if we go from alkyl halide to alkene, then we could be a little bit more regioselective in how we add the bromine back to the alkene. And so this sequence of steps, we go from an alkyl halide to an alkene via elimination, and then we carry out a subsequent addition reaction to give us our final target molecule, our target alkyl halide. So this is how synthesis is carried out. It's taking one-step syntheses, if you will, and combining them in a particular order such that we can get a particular outcome. Now let's look at some examples of how we could do this. So You can see here are some synthetic strategies. This is considered a synthetic scheme. This is how we could carry out this particular synthesis. So starting from this particular alkyl halide, if we use sodium ethoxide, remember the active species is the ethoxide ion. The ethoxide ion is going to give you, in reacting with an alkyl halide, it will give you the more stable alkene, the more highly substituted alkene, as we saw previously. And so as a result, this will be the major product of that reaction step. So this one-step synthesis, we would expect this to be the major product because this is the more highly substituted alkene. Now, if we were to carry out now an addition reaction, hydrohalogenation of this particular alkene, we would add regioselectively the bromine to the more highly substituted carbon of that alkene. And we saw that was due to the stability of the carbocation intermediate that's formed in this first step of this reaction, this first proton transfer step. We generate the more stable carbocation, and then the bromide comes back in a nucleophilic manner to give you this particular alkyl halide. So again, sodium ethoxide is used in an elimination reaction, E2, and then we have the addition hydrohalogenation of the alkene to give us our new alkyl halide. So that'd be one synthetic strategy that we could use to form that particular alkyl halide. And at this point, that would be the only way we could do that effectively. Now you can see that there's other pathways that if we choose to take them, we could carry them out, but we wouldn't end up with the same target molecule that we're after. So just as an example, if we took this same alkene and now we added HBr, but in the presence of an alkyl peroxide, we wouldn't obtain this as our final product. We would, in a sense, just regenerate our initial reactant. Because remember, the regioselectivity of this reaction places the bromine atom at the least highly substituted or less substituted carbon of that original alkene. So it ends up placing a new carbon-bromine bond here. And again, the difference between these two reactions has to do with the mechanism, that this was an ionic mechanism, whereas this was a radical mechanism. So a difference in mechanism would give rise to a different product. You can see that if we were to choose a different base to start off this synthesis, if we were to use the tertiary butoxide, potassium tertiary butoxide, here again we see that there's regioselectivity associated with the formation of the alkene, that the alkene wouldn't be formed as we saw in this first example, that we would form an alkene in this particular position. And again, this has to do with the fact that the bulkiness, the steric hindrance associated with this base, these beta hydrogens are more likely to undergo a reaction via E2 as opposed to the beta hydrogen at this position. Not to say there'll be some minor product associated that will give you this, but the major product, which is what we're generally interested in, will be this particular less substituted alkene. Now, if we were to add HBr in the presence of an alkyl peroxide, you can see that you get a very different alkyl halide. We're going to add the bromine, the new carbon-bromine bond will be at this position to give you this particular alkyl halide. Now, if we were to add HBr to this scenario, we would end up with our original alkyl halide. So again, if we were to add HBr in the absence of the alkyl peroxide, we would expect the new carbon-bromine bond will be at this position. We might even get rearrangement that would involve the bromine going to this position as well. So we would see a bit of a mixture. We would see some, most likely the major product would be this, but we would end up with also some of our original starting material being produced. So the path that is best, if you will, if you're comparing the atom efficiency, the atomic economy as they refer to it, as their atom economy, this would be the favored pathway to carry out this particular synthesis. So this is how we strategize about carrying out syntheses for specific target compounds. So now let's look at a different synthetic strategy, one in which we want to change the position of a pi bond. And again, this could be carried out in 2 steps using reactions that we've looked at previously. So in this example, we have a methyl cyclohexene, 1-methyl cyclohexene. And if we carry out the addition reaction on this particular system, you could imagine we could add a good leaving group to it. And so we form an alkyl halide in this particular example. Now, again, using our knowledge of regiochemistry and regioselectivity, knowing how reagents interact with alkyl halides, we could choose the appropriate elimination conditions to give us a pi bond at this location. So again, we can't go from this to this in one step. This is not, possible, but it is very possible to carry out the reaction in a sequence of steps, in this example, in 2 steps. So we call this a 2-step synthesis. So let's look at how we could carry this synthesis out. So starting from our methyl cyclohexene, if we were to carry out this reaction in the presence of HBr, we would see that we'd have some regioselectivity in which the bromine is added to the more highly substituted carbon of that original alkene. Using a bulky base, potassium tertiary butoxide, we could regioselectively place the double bond at this position via an E2 elimination or an E2 reaction. So that would be the most straightforward way of moving the pi bond to this particular location. Now again, the choice of base is very important. If we were to choose a less bulky base like sodium methoxide, sodium methoxide, sodium hydroxide as well would work, we would generate the original alkene. So there'd be kind of a make work project and you would really not get to the target system that you're after. And what's shown below is just other pathways that could be taken using similar reagents. So in this bottom example, we see if we added HBr in the presence of an alkyl peroxide, we would place our bromine atom at this position, the least highly substituted position of that original alkene. And so a choice of base is not going to get you to this very easily. You're going to see that if we were to choose the bulky base, we're going to end up with a double bond at this location because this hydrogens at this location are less sterically encumbered. It's a secondary position versus a tertiary, for example. So most likely that you'll form as a major product this alkenyl product. Now if you use a less sterically hindered base, then again we would return to our original alkene, but that wouldn't move the pi bond to this location. So there's no carbocations formed when strong bases are used, and so we're not going to have the same type of rearrangement that could be possible in that previous synthetic example. So similar to the last example, this top pathway is the most efficient pathway, really the only pathway with the current reagents that we've looked at to obtain that double bond in that particular location. But as you can see, we couldn't carry out this transformation from this alkene to this alkene. These are constitutional isomers of one another, but the movement of the pi bond requires 2 separate reactions, 2 sets of reagents to carry out this complete synthesis. Now this chart may be a little bit overwhelming at first glance, but it's a nice summary of what we've covered to this point and where we're going in terms of what we have left to explore in terms of functional group transformations. And I find this chart, which is found in your text, to be quite helpful when you're carrying out synthesis, synthetic strategies. And you can see that, our first real dive into reactions, we started after, acid-base reactions, our first real dive was in starting with alkyl halides. And we saw ways in which we could carry out substitution reactions to generate alcohols. And we saw ways in which we could carry out elimination reactions to form alkenes. And so we have this knowledge now of how we can transform alkyl halides into the alcohols or into the alkenes. Now, likewise, we've also learned in this particular section ways in which we can take alkenes and add different molecules to them. So if we take an alkene and undergo catalytic hydrogenation, we can form alkanes. We've also seen many ways in which we can take a alkene and transform it into an alcohol. We saw 3 different methods. We have acid catalyzed hydration, hydroboration oxidation, and oxymercation demercation. So we saw, yes, there's differences in product outcomes, regioselectivity, stereoselectivity, but we covered 3 methods to form an alcohol. Likewise, we saw in the previous section that under strongly acidic conditions and heat, we can transform alcohols to alkenes. As well, we can undergo some functional group transformations. We'll talk a little bit more about this in a later section, but making the alcohol a better leaving group in the absence of acid, we can also carry out this transformation, but we'll cover that one at a later time. And we've also looked at ways in which we can take the alkene and go back to the alkyl halide, either using HBr or HBr in the presence of a alkyl peroxide. So we're going to be continuing to fill in the details of this particular chart, and that will help us with our synthetic strategies. It'll allow us to see how we can get from one region in this chart to another. So going into the next section, we're going to be looking at reactions that of alkynes as well as reactions that produce alkynes. And so you can see we're going to examine how we can go from an alkene to an alkyne. So as a result of building up these one-step syntheses, we'll be able to develop strategies in which if we start with an alkyl halide and we want to form an alkyne, well, there's a few ways we could do that. We could go alkyl halide, alcohol, alkene, alkyne, or we could sidestep the alcohol and go directly from alkyl halide to alkene to alkyne. And so this is the method or the approach that we use when carrying out synthesis. So there's more to come, but we're starting to build up our knowledge of one-step syntheses, and so applying that knowledge into multiple-step synthesis is really the end goal of this course. And so if you have any questions about how to predict the outcomes of addition reactions or questions about how we develop these synthetic strategies, by all means, send me an email. Thank you.